Welcome to today's session, Flexible Bayesian Approaches in Imaging Analysis. And I'm so excited because we have three excellent speakers in today's session, three very eminent researchers in our field. Michele Guindani from UC Irvine, Professor Marina Vannucci from Rice University, and Professor Jeff Morris from UPenn. So I'm really excited about this session. Without further delay, we'll get started. So the first talk is by Michele, and he's going to talk about Bayesian time-varying tensor vector autoregressive models for dynamic effective connectivity. Each speaker has 20 minutes, so Michele, I might just give you a heads up around the 18-19 minute mark. Okay?
Perfect.
Please.
Let me organize a bit my Zoom here. Perfect. Can you see my slides?
Yes, we can see your slides.
Perfect. Thank you. So let me start by thanking Suprateek for inviting me to this session and thanking him for Suprateek as well for organizing this conference. I really enjoy seeing lots of known and familiar friends' name in the audience. I really miss seeing you also because I have to confess that I'm teaching these days, so after my session I will have to go teaching, and it's not the same experience as I'm used to when I meet you guys in conferences. So this is a talk that is based on some recent work that I've been doing with Ivor Cribben at University of Alberta, Sonia Petrone at Bocconi University, and the horsepower of this talk is indeed a bright student from Bocconi University, Wei Zhang. He was a pandemic visiting a student at UCI, meaning that he came to UCI, but we basically met all the times by Zoom because he was home. So you know how these things go. So what I'm going to talk about today, let me see if this works. Oops. Okay, is brain connect is a model for vector autoregressive a vector regressive model for dynamic effective connectivity. Brain connectivity is studied in multiple ways with fMRI studies. Of course, there is no need to discuss this with this audience, but just as a remark, as a reminder, so one may be interested in structural connectivity that maps the Y-matter tracks that physically connect brain regions. One may be interested in functional connectivity that studies undirected statistical dependencies between brain regions. Here today, we're going to discuss about effective connectivity that tries to describe, identify direct influences from one brain region to another. So there are many approaches to effective connectivity inference in neuroimaging, in fMRI studies. And here I mention just a few: dynamic causal modeling, structural equation modeling, the use of Bayesian networks. I'm going to discuss today a Bayesian VAR approach that is based on the idea that the cause precedes and help predict effects temporally. So basically on the idea that direct influences, and if you want causality, is described by what goes under the name in time series literature of grandeur causality. Of course, the type of relationship that we will describe will be based on the hemodynamic response. So in this regard, of course, we won't be able probably to pinpoint direct neural dependencies. So in terms of studying effective connectivity, typically, a model that is often used is the vector autoregressive model framework. Here we are assuming that we have a n-dimensional vector of representing a fMRI Ball signal recorded at different voxels or regions of interest. And typically the interest is in trying to identify the connectivities between brain regions for each leg through the elements of the coefficient matrices A. Now, there is, of course, an increasing realization that the brain connectivity is by nature dynamic and fluctuating, and the connectivities may not be stationary over time. So there is a realization that we should go from a framework where these A's are seen as static over the entire course of experiment to a framework where we allow these A's, these matrices, to change over time. Just as a remark, there has been a lot of work recently in functional connectivity, especially to understand the dynamic functional connectivity, and there are a few works that appeared in the literature, both statistical and neuroscience literature at this regard. Here I'm going to focus on a model for dynamic effective connectivity. And in particular, with that, basically, I'm just going to assume and I'm going to consider a case where I have basically the matrices A's are indexed by a time index. So basically, they're allowed to change over time. Of course, this framework creates some challenges. We need to try to model transitions between the varying connectivity states with the different times, and we would like to basically create a framework to model these transitions in a sparse way. So we, in order to deal with the amount of parameters that we introduce by modeling the A's over time, we needed to assume some sort of regularization at each time in over the P legs. There is also another issue that we want to tackle, and it is the scalability. Vector autoregressive models often suffer from scalability issues. So how to maintain the computational feasibility and uncertainty quantification, especially when we have to deal with so many ROIs. So what we're going to propose today is a computationally efficient, for us, from our perspective, time-varying Bayesian vector autoregressive model for modeling high-dimensional time series, allowing a parsimonious representation of the dependent structures. So we do this by basically using a series of tricks. And in particular, the first trick is allowing a later representation of a VAR coefficient. The idea is that at any given time, the VAR coefficient matrices are obtained as a mixture of only an active subset of components. Basically, the idea is that we have a set of latent base matrices that are activated at each time, and the composition of which is going to create the dependence over time. This is, of course, a first important reduction or representation of a model, because, of course, the latent base matrices are not changing over time. It's only a binary indicator of latent individual experimental conditions that will indicate if a particular latent base matrix is active at a particular time. So what we have is indeed an indicator of latent individual experimental conditions that will at each time will indicate which one of the latent base matrices are active. So this is, of course, the attention now goes into this gamma HT that models the latent transitions. So the time variant activations of the latent base matrices in the VAR. In the neuroscience literature, what has been used typically to model time varying transition has been hidden Markov models. On one perspective, especially when the number of states increases, and typically to take into consideration multiple different variance coefficient matrices over time, we may expect a lot of states. Of course, the hidden Markov models may not be as ideal because they may require too many parameters to estimate. So instead of that, of reverting to hidden Markov models, we're going to use here a Eisenhower specification. This Eisenhower specification retains the Markovian dependence, allowing varying activations over time. and also has a parsimonious parameter representation because it depends basically each of the distribution of each time series of indicator is going to depend basically on two parameters. One set of parameters that defines sparsity, and another set of parameters that defines interaction between the gammas. So this results in a parsimonious representation of the transitions and the probability of transitions, of course. In particular, it can be shown that this Eisenhower representation corresponds to a discrete ARMA model, in particular what are called new discrete ARMA model in the terminology used by Jacob and Lewis in 1983. This is important because it allows some consideration in terms of prior elicitation of for the parameters thetas and kappa in the Eisenhower. I'm not going to have time to go through the details, so I will leave it at that. The second way in which we are able to deal with and reduce the number of parameters considered in the time-varying representation is by using a low-rank representation of the VAR coefficient models. And in particular, what we're going to use is, is that we assume that the base tensors that characterize the base matrices in the composition of the VAR coefficient matrices are actually admitting a rank 1 parameter decomposition. And we recognize in particular three margins, the two tensor margins that basically relate to the dimension of the VAR matrices, and one tensor margin that relates to the lag mode. So what we eventually are left with is basically a rank H parameter decomposition to represent the VAR coefficient matrix at each time, with the difference and with the point that, of course, the different elements of rank decomposition are activated differently at different times due to the effect of the latent indicator. So we are not really interested here in the identifiability of single tensor margins. Of course, what we are interested in is indeed recovering the temporal pattern of the VAR coefficients, that is the product of the margins, and in particular, possibly also the latent base matrices. So an important point is that we basically reduce the number of parameters that are considered by using these tensor representation to a number that is linear in the observation size n with respect to the n square order that we would have without considering the tensor reparametrization. We want to induce sparsity, not only through a parameter decomposition, but also by achieving further shrinkage by putting sparsity-inducing priors on the tensor margins parameters. These will eventually allow us a more interpretable estimation of the connectivity patterns. And here we're going to use two types of sparsity-inducing priors. In particular, for the tensor margins that depend on the number of a dimension, alpha 1 age, alpha 2 age, we're going to use a multi-way Dirichlet generalized double Pareto prior. This is a type of priors that has been used a lot in Bayesian tensor regression, and has been shown as particularly favorable in determining or inducing sparsity in complex structures, in factor models, basically. The second type of sparsity-inducing prior is going to apply to the third tensor margin, alpha 3 age, which captures the lag parameters. Here we want to somehow learn about the order of the lags. And for this, we're going to use an increasing shrinkage prior that has recently been proposed by Legramanti, Durante, and Danson, which basically allows higher order lags to be penalized. So we reuse their prior to basically select a small number of lags into vector autoregressive structure. The basic idea here is that the elements of the third margin are sampled from a spike and slab prior, where the weights of the, let's say, zero component are going to increase for larger lags. So it's going to be, if it's going to be a larger, higher probability to select zero or a value close to zero for larger lags. I see that my time is already reducing quite a bit, so I'm going to go fast and just give an idea about the posterior inference. Of course, we are going to sample the parameters from the Ising prior. This requires a metropolis Estin algorithms where the normalizing constant depends on the sample parameters, so we will need to use approaches that have been proposed to take into account doubly intractable distributions. We have done a simulation study, multiple simulation study to investigate the performances of our model. In particular, in these simulation studies, we have considered increasing dimensions of the VAR matrices, or basically of a VAR model, in particular by considering n equal to 10, n equal to 40, and n equal to 100. We have also tried to compare our fit with the fit of a TV-reg package in R. This package uses kernel smoothing techniques to estimate the VAR coefficients. I will note that for n equal to 100, the TV-reg approach, which works relatively well, showed numerical problems, whereas our method was able to recover the structures similarly as in the lower dimensional cases. So for the first simulation study, we simulated 10 time series from our model. I'm going to show you these quite fast. We assumed a misspecified values of the number of components in our model and the number of lags to assess our ability, our method's ability to determine the true rank and lag order of a VAR model. And these are some results. I'd like you to focus on basically, well, of course, due to the regularization, our model is able to capture better the structure of the VAR coefficient matrices over time. We are considering basically a metric based on the square root of the average Frobenius norm between the posterior mean and the true matrices across 100 data sets. So we also are able to assess the uncertainty of our estimates. Here, I would like to point out the differences, the true zero entries between our model and the TV-reg model. This is clearly an advantage, this improvement is clearly an advantage of the regularization that is provided by our model versus the TV-reg model. I went back, sorry. We also considered performance evaluation of a posterior estimation of a component indicator. We do relatively well, except maybe for some loss in specificity, which is not too much of concern, especially due to the fact that these latent-based structure is somehow weakly identified. I'm going to skip over the simulation for n equal to 40, except that here we have also some pictures showing the way in which we recover the structures active at different time points. And it looks like, so this is the truth, this is our posterior estimates at different time points, of course, averaged across the MCMC iterations. And it looks like we were able to recover the structures quite well. And here I had also a picture depicting the gamma's coefficients over time. And it looks like, so for example, this component here is not active. Indeed, if you remember, we had misspecified the model by assuming h equal to 4 when the true components were actually 3. So In the data analysis, we consider a fMRI data set where participants were asked to read chapter 9 of Harry Potter and the Sorcerer's Stone. This is a very active and full of twist chapter. In particular, here we're going to consider a topical moment in the plot and we're going to consider basically 2 runs of experiment. We set p equal to 4 and h equal to 10. And I just wanted to notice that through the tensor factorization, we're going to decrease the number of estimates parameter from almost 2 million to 7,000. And of course, a further reduction is achieved through the sparsity-inducing prior. I have less than 1 minute left, so I won't have time to read about the first flying experience of Harris, which is the first topical moment that we're going to discuss. And I hope that I can show you. Open. Well, this is just a video of the time varying connectivities across 4 lags that we are able to recover. As you can see, there is something happening at different time points, right? So so far, this of course is peculiar. It's difficult to see and to identify structures in this way. I want just to make sure that you see the effect of the lags. At lag 1 is the most prominent. The other lags are decreasing. The effect is somehow decreasing over time. So let's see if I can go back. I'm not a pro in these things to the presentation. Perfect. Okay. 10 seconds left. It turns out that actually we are able to identify some important structures or some important connections in the time-varying patterns, some patterns that are persistent before and after the flying experience, as well other patterns that change between before and after, and patterns also different between subjects. I don't have more time, so I just wanted to say that this is, again, a work that is being done with Ivor Cribb and Sonia Petrone and Wei Zhang. It's going to be soon to be archived. We have just to correct the last typos in the paper. We have possible extensions, quite a few of them, extending to multiple subjects, incorporating available information. Through, for example, structural fMRI, but also use what we find as predictor for clinical or behavioral outcome. And with that, I stop.
So I think next up is Professor Marina Vannucci at Rice, and she has she's presenting. Her topic is Bayesian inference for stationary points in Gaussian process regression models with applications to ERP analysis. Yes.
All right. Thank you. So I assume you can hear me and you can see the slides. So thank you for the invitation. This is a joint work with Mang Li and Zijian Liu at Rice University, and with Changhan Hu, who was a postdoctoral fellow at Rice, and he's now an assistant professor at Marquette University. And it's about some work that we did on the analysis of ERP data. So I'll start by motivating the work with the application, and then I'll show the method which we have implemented, which is a derivative constrained Gaussian process regression for the detection of stationary points that would allow the localization of interesting components in the ERP signals. It's a Bayesian approach, so I will go through the description of the prior, in particular the prior on stationary points. Inference here is very straightforward. We can do inference through a Monte Carlo EM. If I have time, I'll show you some preliminary results on simulated data, and for sure also I'll show you the results on the case study. So in ERP or event-related potentials, we essentially averaged EEG signals which are time-locked. So we looked at EEG signals recorded in response to external stimuli, and the ERP waveform is obtained by averaging across trials, oftentimes also across subjects and across multiple electrodes in an effort to wash out the noise. And so once we average across a number of EEG segments, we get a signal or a ERP waveform of the type that you see up here highlighted by my cursors. Oftentimes in the experiments, the interest is in localizing the different features of this ERP waveform. In particular, you see these components highlighted, P1, N1, P2, N2, and so forth. And these components are often related to specific cognitive processes of interest. Here in particular, I will be looking at an experiment where the subject is hearing some words, and so we will be looking at words recognition type of cognitive processes. So again, the main interest in ERP studies to identify those ERP components, which oftentimes are kind of dips or peaks in the signal. So in particular, for every component, the characteristics of interest will be things like the latency and the amplitude of a particular component. So if we look at a signal and look at these components, we are actually looking at trying to locate latencies and amplitudes of stationary points of that particular signal. Traditionally, the data are averaged over number of trials and number of signals, as I said, in an effort to wash out the noise, and then the characteristics of the ERP components are kind of found by visually analyzing those signals, and of course this procedure kind of lacks of uncertainty quantification. So in our approach, we try to formalize the method through a model, a statistical model that would therefore allow a quantification, an estimation of the location of the stationary points, as well as a quantification of the uncertainty about those estimates. So let's look at the model. So it's essentially a shape constrained regression. So it's a non-parametric regression of the type y equal to f of x plus epsilon, where we impose some constraints on the first derivative. So we assume that there is a number m of stationary points where the derivative of the signal is equal to 0. And unlike many type of non-parametric regression models, the interest here is not so much in estimating the function, but in locating the stationary points, T1, Tm. Although as a bonus of the approach, we also get an estimate of the non-parametric function f. So again, in the ERP applications that we're working with, yi is the ERP time series data, and for a given subject, and f is the true underlying smoothed ERP waveform, and the t con m are the stationary points of interest. We model the unknown function f by a Gaussian process prior, where we assume a constant mean function and a covariance function of the type that you see on the slide. There are many possible choices for this covariance function, and here today I will be showing you results that use the so-called exponential kernel, which is a squared exponential kernel, which is a relatively smooth kernel. We've also investigated other kernels like the matern kernel, but we find that for ERP data, the squared exponential seems to be working pretty well. And the reason can be seen if we actually look at the type of functions that can be sampled via this type of kernels for different values of the hyperparameters that characterize the kernel itself. So you can see we can get fairly smooth signals that look like our ERP waveform, as well as more noisy waveform that we might be getting if we consider doing less averaging of the EEG signals. Okay, so in the model, as I said, we impose a number of stationary points. So we impose a zero derivative on a number of points T1, Tm. A nice feature of using Gaussian processes is that the derivative of a Gaussian process is also a Gaussian process. So once we impose a GP on F and we impose a zero derivative on the stationary points T command, essentially we obtained what we call a derivative constrained Gaussian process, which is not new in the literature. There are, people who have investigated this type of processes before, like Jim Berger at Duke. And so here we, our derivative constrained Gaussian process will be characterized by the mean function that you see up here on the slide and the covariance kernel that you see I'm highlighting with a cursor, which can be obtained from the mean function and the covariance kernel of the original GP. Okay, so this construction is pretty simple to handle. So now on to the priors. So as I said, the interest is in the stationary points, so in the latencies T1, Tm. And one challenge in this type of problems, particularly perhaps from a Bayesian point of view, would be to try to handle the case of an unknown number of stationary points. And here is where I think our method becomes interesting, because we actually realized that we could simply impose a univariate prior on T, so simply have a univariate prior on T, and this simple prior induces a posterior distribution, which is actually multimodal. It's actually, we can actually prove theoretically that the posterior distribution of T will tend, for n that goes to infinity, will tend to a mixture of m Gaussian components, each one centered on one of the m stationary points. So this simplifies the inference incredibly, because now we can we only have a univariate T. We have a univariate prior on T that can be a simple uniform distribution, and then we automatically get a multimodal posterior that automatically selects the optimal number of stationary points, and then via inference on the modes of this posterior, we can estimate the latencies of these m stationary points. So the method turned out to be incredibly simple to implement. As I said, we have a paper with a theoretical results that shows the multimodality of the posterior distribution. But also today I'm going to show you just results that we obtained on simulated data and real data by using a sampling technique, which is a very simple Monte Carlo EM estimation method that essentially, I think I have one slide of this, yes, that essentially uses a stochastic step where we sample T and we sample sigma squared, the variance of the error term, and then we optimize an M step where we optimize the parameters of the squared exponential kernel, essentially via empirical base estimation. So it's a very straightforward procedure that produces a sample on T, a sample on sigma squared if we want to check on the inference on sigma squared, and an automatic tuning of the hyperparameters of the model. So I have 9 minutes. Okay, so let me see. Okay, let me first show you the results on real data. And then if I have time, I can go back to, because I think I care about the application more than the simulations. So the application is on data that we have available from an investigator here at Rice University, Simon Fisher-Baum. He's a psychologist, actually, and he studies the way that people understands words. And so in this particular experiment, there are two pairs of lexically biased voicing continua. They are created by composing a lexical pair of different types, where one extreme is given by a known word and the other extreme is a nonsensical word that sounds like the true word. And you have a few examples here. And so the subjects listen to these words, continual words that are spoken to them, and they are asked to choose which endpoint the token sounded most like, the voiced endpoint or the unvoiced endpoint. And in the experiment we had, I think it's the other, okay, we had a number of subjects, and we had a number of young people and a number of adults. And one of the aims of the experiment was to see whether there was a different level of understanding between the two different age population, as it should be expected. We had about 2,000 trials, which we averaged within each condition. We also selected 6 electrodes and averaged across the 6 electrodes within each subject. And here on the plots, you can see some of the data. In the old trials, you see the data by subject. Again, average over trials and over 6 electrodes, all the subjects. While in the second plot, the plot on the right, you can see the same data, but also plotted the averaged ERP waveform by the two different populations of subjects that we have, young and elderly. And you can kind of see, right, looking at the average waveforms, you can kind of see that the stationary points seem to have slightly different latencies. So the idea is, can we analyze the subject level data to sort of, recover that result, but also with uncertainty quantification. So we fitted our model, kind of an extended version of our model to handle multiple subject data to the, there it is, to the 11 young people that we have, college-age students, and the 11 older controls. And the method gives subject level inference as well as group level inference. At subject level, you have here just an example of an output on one of the subjects. This is the same subject doing two different types of stimuli, and you see that the output of the method produces, as I was saying, an estimate of the ERP waveform, as well as a posterior distribution of T, which is the stationary point. And as you can see, the posterior distribution is clearly bimodal, although a priori we just allow a univariate T. It's like saying that we expect at least one stationary point, and that the posterior kind of finds the correct number of stationary points, which is 2 in this case. And then by looking at HPD regions for the posterior distribution, we can actually calculate a certainty around the estimation of these stationary points. So this is for one subject. And then if we repeat this for the 11 subjects, 11 young subjects that we have and the 11 older subjects, then we can we can compare estimates across the two different groups. And so here in particular, you have estimated stationary points with HPDs intervals for each one of the 11 older subjects and each one of the 11 young subjects. And I think the dashed line indicates the overall stationary points. And so I think, for example, you can see that in the older population, the kind of latency seems to happen a little bit later than the young population, as it should be expected. Okay, so yeah, so I think I'm good with time, and I can go back to the simulated data if there are questions later on. So we have proposed a Bayesian model to impose and infer localized shapes of an unknown function. It's suitable for the application, for the analysis of ERP waveform, and it produces a posterior distribution of latencies of ERP components, as well as estimation of the ERP signal. We have proven the asymptotic behavior of the posterior distribution. In particular, we have a result on a generalized from Mises theorem that essentially proves the multimodality of the posterior distribution. We're working on, we have an R package, but we're working on an R-Shiny software so that the method can be actually used by practitioners. I said the sampling procedure is really easy and very, very fast. And of course, the next step in this process, in this line of research, will be to extend the model to possibly avoid the averaging across trials, so to have not just a subject level, but also subject and trial level type of modeling. And that's it. I think I already had I already acknowledged Zijen and Chanhan, as well as Mang, sorry, which is not on this last slide, and the collaborators Simon Fisher-Bond and Colin No at Rice University. Thank you.
The next speaker, Professor Jeff Morris from UPenn, and his talk is titled Connectivity Regression.
All right, well, thank you again for the invitation. Wait, sorry, let me make sure I'm sharing okay here. Okay, so are my slides visible here?
Yes, we can see your slides.
Great, okay. So, so what I'm going to talk about is connectivity regression, the idea of looking at brain connectivity as it varies with covariates. And so this is joint work with Veera Baladin-Dayuthapani and our joint PhD student at Rice, Neil Desai. Okay, so so the connectivity problem we're going to look at is functional connectivity, and I know here I don't have to overview functional MRI, and I'll just mention we're looking at the functional connectivity problem, and there's many different measures that can be used to quantify functional connectivity. We're going to look at Pearson correlation, which is one of the most commonly used ones. Okay, so I'll start with a motivating example and talk about our method that we're going to develop for this. So, so we have data from the Human Connectome project, and in particular, there's resting state bold signals for just over 1,000 healthy young individuals. And so we're going to look at connectivity on regions of interest defined by the group ICA components that are there on the Human Connectome site. So here we have the 15 components we are looking at. So we're going to look at connectivity across the bold signals in these regions of interest as it varies with covariates. And so for our illustration, we're going to look at several covariates with language processing, as well as anatomical areas from known functional connectivity hubs in the brain. Okay, so looking at regions of interest, we can think of our data here for subject I, for region K, and for time point T as YITK. And so we're going to use as a measure of connectivity the correlation between the data for region K and K prime. And we get an estimate of connectivity for each subject I. And conceptually, what we would like to do is fit a regression model to relate this to covariates. And specifically, we would like to determine which covariates appear to affect the connectivity. And then for those covariates, which edges appear to be the key differences across covariates. So we want to do this thing sort of jointly across the entire correlation matrix. So of course, to fit this type of regression model, we have a lot of challenges. The scale of the data being -1 to 1. If we want to fit the whole correlation matrix, we need to honor the constraints of the correlation matrices. We also need to think about what type of distributional assumptions and inference are reasonable to make. And also, we would like to handle potential edge-to-edge correlation, which I'll motivate here in a minute. So, so this idea of connectivity regression relates to a large and growing literature in the last 5 or 10 years involving graph or some older literature on covariate regression. So there's a lot of literature looking at regression analyses on graphs, particularly for Gaussian graphical models. There's a large number of papers that look at estimation and comparison of graphs between groups. So you can think of that as regression with discrete covariates. And then there's also some general regression frameworks for graph edges in various ways that have been done. There's also a literature on covariance regression, looking at regression of covariance matrices on predictors. And so a lot of the early work was for sort of ordered multivariate data, like time series or longitudinal or serial regression that is not invariant to the ordering of the variables. But there's also some literature on general covariance regression, including a paper by Hoff and Niu. And there was an old paper here that looked at a log matrix transform that I will mention here because our approach will utilize this transform as well. So, so this is the literature here. And one important distinction to make when thinking about this type of regression problem is what type of data do you have? Do you have vector value data, or do you have matrices from which you can construct entire correlation matrix objects? Much of the literature that I mentioned there in the graph regression space is for vector value data, where we get a single K vector for each subject, and we want to somehow look at the associations across those K categories with subject-specific covariates. But our setting here is a little different, where we have an entire matrix because we have the time series. So from this, we can estimate an entire subject-specific K by K correlation matrix. And much of that literature is not specifically looking at that case, and in particular isn't taking advantage of some of the key benefits that we can have and structures that we can take advantage of in our modeling. And so in particular, we can consider the correlation matrix as sort of an object, sort of akin to the way we think about functional data analysis, and learn the within object correlation structure, which can allow us to gain efficiency by borrowing strength. So what do I mean about within object correlation in this case? Well, what I'm talking about is edge-to-edge correlation or correlation of correlations. So I'll do a toy example here to illustrate what we're trying to do with connectivity regression and what I mean by sort of this second order correlation or edge-to-edge correlation. So let's just take a simplistic example where we have 3 brain regions representing a visual, an emotional, and a memory center. And let's say individuals represented with the Band-Aid have had some trauma in their past that is expected to be triggered maybe by a particular image. So let's say we show that image to people, and then we look at the connectivity of these 3 regions, how it varies across individuals that have and haven't had the trauma. So here the thickness we have the triad here, and the thickness of the edge measures the degree of association there, or the connectivity. So we can see here that in this simplistic example, there's greater connectivity for people who've had the trauma than for those that haven't. That's the type of thing we want to discover here. But the other element that I put in this simple example is that all three of these edges tend to be correlated with each other. They're either all thick or they're all thin. So that's, and so this is kind of what I'm talking about, a second order dependence, or a correlation of correlations. When you have subject specific correlation matrices, you can actually estimate this from your data. And it's not clear that, and this association can be part of the subject to subject heterogeneity that you can learn from the data and take advantage of. So we would like to do that in our regression framework. Okay, so how are we going to build a regression for this context? Okay, well, first of all, we're going to estimate subject-specific correlation matrices, and at first we're going to condition those on those as our data. Later on, we want to, of course, take into account the uncertainty of the sampling distribution of those estimates. But for now, let's just say we observe these correlation matrices. So the first thing we're going to do is we're going to map to the Fisher space using a log matrix transformation, which is a multivariate generalization of the Fisher transform. So what are we doing here? Well, if we have a symmetric matrix sigma, the matrix exponential can be defined as a matrix generalization of the exponential function with this infinite sum. And it can be shown that for a positive definite sigma, we can define the inverse operation of this matrix exponential as a matrix logarithm, which we can compute by taking the log of the eigenvalues after a decomposition of the matrix. So this is a very useful property if we want to do regression on these covariance matrices or on correlation matrices. And the reason for this is if we have a real and symmetric gamma, that guarantees then that the sigma will be positive definite. This transformation is invariant to the reordering, so does not require ordered data. And it can be shown that this is a multivariate generalization of the Fisher transform that's been commonly used. Tom talked about it in his talk. And there are results that show that this transform makes the data approximately Gaussian and weakly correlated. And this Archikova and Hansen paper shows how you can adapt this for correlation matrices, so that if sigma is actually a correlation matrix, you can do a similar thing. So what we're going to do then is let R sub I then be our k by k correlation matrix for subject I. What we're going to do is consider a decomposition of the matrix using a spectral decomposition, and then take the log of the eigenvalues. That's what gives us the log matrix transform matrix. Then if we take the lower triangular elements and vectorize them, these are what we're going to call the Fisher correlations. So this is going to be a mapping of the correlations into this Fisher space. So this vector, just like the unique correlations, the lower triangular correlations, is of length m, which is k minus 1 over 2, if we have k different categories. And so based on this, any real vector gamma will induce a valid correlation matrix R if we do the inverse transform. So this is very useful for simulating data, but it's also going to be useful for our modeling. Since we have Gaussian assumptions, because of the properties of this transform, it's reasonable to perhaps make Gaussian assumptions on this vector, which is convenient for modeling. And also, if we think about this m-dimensional vector in a multivariate space, the covariance matrix in that space captures the edge-to-edge dependent structure. That's sort of that correlation of correlations I was talking about, that over-dispersion that we would like to take advantage of. Okay, so once we map then to this Fisher space, now we're going to fit a multivariate regression in this space. So we have this m vector that's assumed to be a multivariate normal, and the mean is going to be a function of p covariates. So we have a set of coefficients that are M by P. So M are all of the edges, P are all of the potential covariates. And then we have this covariance, omega, that is the M by M. Here I have it written as a precision matrix. This captures the second order correlation structure in the Fisher space. So what we're going to do is we're going to model this. Now you could assume diagonal and independence in omega and make this thing speed up. And we're going to have that as a comparative method. But what we would really like to do is do a multivariate approach where we take into account this correlation, which will give us advantages. So first of all, is this correlation evident in the data? Well, if you look empirically at the data, this is from our 15 by 15 data set. Each row and column here is one of the edges. And this is just the second order correlation. If we compute the Fisher variables for all n subjects, and then we just look at the empirical covariance matrix and sort of reorder it, this is what we get. And you can see there's substantial correlation where this group of edges is positively associated with each other, these are associated with each other, and then they're negatively correlated with these groups. So this is the type of second order correlation that can be evident in these data that we want to take into account. So why do we want to take this into account? Well, basically, by doing this, we're taking into account the correlation within the object. So sort of analogous to the calculating and accounting for correlation across T in functional data analysis, accounting for this correlation should give us increased statistical power for inference on beta, especially when we're talking about joint inference. Also, this picks up on the concept of seemingly unrelated regression that kicks in here that suggests that our estimates of these regression coefficients beta should be more efficient because we're taking into account this correlation. Okay, so this is just a standard multivariate normal distribution here, but there's pretty high dimension here where the beta vector is order pk squared and the omega vector is order k to the fourth. So we need some sparsity. So we want to impose some sparsity across B and omega. Okay, and the way we're going to do that is by using a multivariate spike slab lasso that was introduced by Deshpande et al. In 2004. And oh, sorry, Siri has a question. So we're going to use a multivariate spike slab lasso to do simultaneous variable selection across the elements of B and omega. And I don't have time to get into the details, but it's basically a mixture of two Laplaces. And there's an optimization you can do to get estimates of that from estimating the posterior mode. Okay, so I'm just going to skip the details for the sake of time here. But that's basically how we're going to fit our model. So we have this multivariate regression model. We're going to incorporate correlations in the model, and we're going to use this multivariate sparsity penalty to select across covariates and edges in the coefficient. And we're also going to select which second order correlations are important to include. Okay, so once we fit this model, then we would like to do inference. And so we're developing a fully Bayesian version of this. But for now, we're implementing an algorithmic version because we don't need to do a full MCMC. We can get point estimates from the optimization. So then we're going to do our inference by permutation test and stability selection. So we have a way to construct permutation tests that for each covariate will give us a multiplicity adjusted p-value for whether that covariate affects the connectivity. And this permutation test is done in a way that adjusts for the multiple testing. Then for the covariates that are selected, we do stability selection to select which edges are driving each covariate effect. So basically we do a bootstrap and we refit this model and we look at the variable selection and we use the stability selection parameter to assess which edges are most important for that, either for the covariate effect or for the second order correlations. Okay, and so we have a simulation study that shows the properties the properties that we have here, and I'm going to skip the actual slides showing the simulation, but I'll just mention what our results show. So these simulation studies are comparing our approach mentioned here to an approach that ignores the second order correlation and just does selection either using a lasso or using the slope, which is an improved version of variable selection, but that also does not take into account the multivariate nature, the correlation of the edges. And those simulation studies clearly show what the theory suggests, that indeed the seemingly unrelated regression principle kicks in, and we gain efficiency in estimation of the regression coefficients by taking into account the second order correlation. We also show good type 1 error control for the permutation tests, and we show better operating characteristics, better power and type 1 error control by taking into account that correlation. And then if we look at the stability selection, we can look at the area under the ROC curve for selecting the correct edges. And again, we can show good properties, and that accounting for that second order correlation improves the results. But one thing I'll comment on is, in some settings, in the simulation settings, if the second order correlation is very low, the sort of the one at a time method still does pretty good. But taking into account the correlation definitely improves things substantially. Okay, so I only have a few minutes, so I'm just going to go to the results, going back to the human connectome data. Okay, so remember here what we're looking at is the connectivity across these 15 regions, relating them to these covariates. And so when we fit this model, our permutation p-values pick out the read English, the precuneus area, and the post-central gyrus as being strongly associated with the connectivity. And then this shows us the stability selection probabilities for each of the edges for each of these covariates. So we can see the read English is driven by these two edges. The precuneus is driven by 4 or 5 edges. And the post-central gyrus is driven by 3 or 4 key edges that seem to be driving the difference. So here I sort of represent our results. So for the read English task, there were 2 edges that were primarily differing across this covariate. So both of them were a negative association between regions 610 and then regions 5 and 7. One of them is increasing with the read English score, the other one's decreasing. So this shows the stability selection. Now, one problem with this is in the Fisher space. So one problem that's been mentioned with the Fisher space is a lack of interpretation, because it's an M-to-M transform. But what we found is that the dominant edges in the Fisher space are also the dominant edges in the original space. So the interpretation is not too bad, but you can also transform the results back to the original correlation space if you want. And we basically get the same results. And sometimes there's some additional ones that pop up because of the multivariate transform, but the dominant results remain the same. So these are the results we see for the other covariates. Now, one last thing I'll comment on here is the second order correlation. So as we fit this model, we also get stability selection values for each pair of edges. So this shows us which the green edges were selected almost all the time, the dark green edges, as being associated with each other. And if we looked at that empirical covariance matrix, or the empirical correlation of correlation matrices, you see that they roughly align with each other. And I'll comment again that this is the second order dependence in the Fisher space. If we take the same edges in the original correlation space, you see that the overall structure is very similar. So while there's not a one-to-one correspondence that in precise interpretation, the dominant edges and the dominant pairs of edges in the Fisher space are also the dominant ones back in the original space. So the interpretation is not as bad as you might think. Okay, and then this just shows these are just a couple of pairs of edges that are strongly associated with 100% stability selection and with a correlation of correlations greater than 0.7. And so we're coming up with some different ways to summarize also which connections are correlated with each other, which we think also has some independent scientific value to assess what the data tells us about that. Okay, so in conclusion, talked about a connectivity regression framework here that involves linear models in the Fisher transform space, where we can make Gaussian assumptions in a justified way, and we can learn and account for the inter-edge correlation structure by the multivariate modeling. The multivariate sparsity prior gives us sparsity and computational speed, overcoming the high dimensional problem, and also can be used inferentially to assess which covariates and which edges might affect the connectivity. And we have multiplicity adjusted inference at the covariate level, and we have some stability selection measures that can help pick out which edges are really driving the differences. The method's reasonably fast and automatic, but one thing is that because of the second order correlation, it doesn't scale up well with really high dimensional data. So if the second order correlation is empirically weak, ignoring the second order correlation, you can still do inference, and it does reasonably well. You sacrifice a little bit of efficiency, but it's possible to do that for speed if you need to. So we have some future extensions we're going to work on to propagate the uncertainty in estimation, relaxing the linearity assumptions in the covariates, accounting for multi-level models in subjects, and also a fully Bayesian implementation, and also incorporating regression of the diagonal variance terms to do a full covariance regression. And again, this could be applied to many different types of data. We applied it to the functional MRI and to those regions, but it could be applied more broadly. Okay, thank you.